In 2017, 8 researchers published a paper titled, "Attention is All You Need." It introduced the transformer. We will follow one translation through the original model, calculate one attention head by hand, and watch the decoder produce its next token. This is Zero to AI Expert, where we learn AI from first principles to working systems. Subscribe and tell me what you want explained next. The title sounds like a complete component list, but the model also contains embeddings, positional encodings, feed-forward networks, residual connections, normalization, and a vocabulary output. We will locate each part and show what attention changes in the numbers. By the end, you should be able to read the central equations in the paper and connect each equation to a visible operation. You should also know which parts of the original transformer survived in modern language models and what the title leaves out. We will stay close to the paper. When we use small invented numbers for teaching, I will label them as invented. When the 2017 conference paper and a later archive revision disagree, I will show the disagreement instead of hiding it. The paper begins with machine translation. Suppose the input is, "I love AI." The desired German output is, "Ich liebe KI." Before the transformer, strong translation systems commonly used recurrent neural networks, including LSTM networks and gated recurrent units. A recurrent network reads a sequence in order. At position 1, it combines the first token with an internal state. At position 2, it combines the second token with the state from position 1. The state continues through the sentence. That design gives order a natural place in the computation. It also creates a dependency chain. The state for token 4 cannot be completed until the state for token 3 exists. Token 3 waits for token 2, and token 2 waits for token 1. A GPU may contain thousands of arithmetic units, but those units cannot remove a dependency that the algorithm requires. The chain also makes long-distance relationships harder to learn. Information from an early word may have to pass through many recurrent steps before it reaches a much later word. LSTM networks and related designs help preserve information, but the path still grows with sequence length. Convolutional sequence models offered another route. A convolution can process many positions in parallel, but one local convolution sees only a limited neighborhood. Connecting two distant positions requires wider kernels or a stack of layers. Attention already existed before this paper. Translation systems often used attention to let a decoder look back at useful encoder states. The recurrent network still carried the main sequence computation. The transformer changed that arrangement. It removed sequence-aligned recurrence and convolution from the encoder and decoder. Attention became the main way positions exchanged information. This is the claim behind the title. Attention is all you need means that the model does not need recurrent or convolutional layers to perform sequence transduction. It does not mean that the entire model contains nothing except attention. The original model has two large parts, an encoder and a decoder. The encoder reads the source sentence. It produces one contextual vector for every source position. The decoder reads the target prefix that is already known. It uses that prefix and the encoder's output to predict the next target token. For our example, the source side begins with, "I love AI." The target side eventually becomes, "Ich liebe KI." The encoder performs this route: source text, token pieces, token IDs, embeddings plus position information, 6 encoder layers, then a sequence of contextual source vectors. The decoder performs another route: known target tokens, target embeddings plus position information, 6 decoder layers, vocabulary logits, softmax probabilities, then the next target token. Each encoder layer contains 2 sublayers. The first is multi-head self-attention. The second is a position-wise feed-forward network. Each decoder layer contains 3 sublayers. It begins with masked multi-head self-attention. Next comes encoder-decoder attention, often called cross-attention. The third sublayer is another position-wise feed-forward network. Residual connections and layer norm surround every sublayer in the original design. This architecture diagram is useful as a map. It does not yet explain a single calculation. We will now send our example through every stage. The neural network does not receive the sentence as the letters that appear on the screen. The text is first divided into tokens and converted to numerical IDs. The English-German model in the paper used byte pair encoding, usually shortened to BPE. BPE can represent common words as single pieces and less common words as several subword pieces. The exact split depends on the learned vocabulary. For the animation, we will display I love AI and the period as 4 pieces. That split is illustrative. We are not claiming those are the exact token IDs produced by the author's 2017 tokenizer. Imagine that the displayed IDs are 31, 842, 1000, 907, and 5. These numbers are invented for the lesson. An ID is an address into a learned embedding table. It does not measure the meaning of the token. Token 1907 is not more intelligent or more important than token 31. The base transformer uses a D model of 512. Each token ID selects one row from an embedding matrix, so every source token becomes a vector containing 512 learned values. If the source contains n tokens, the embedding output has shape, n by 512. During training, the values in the embedding table change. Tokens used in similar predictive contexts may develop useful relationships in this space. The table does not store a dictionary definition in plain language. It stores numbers that help the complete network reduce its training loss. The paper shares one weight matrix across the source embedding, target embedding, and the linear transformation before the output softmax. That technique is called weight tying. The paper also multiplies the embedding values by the square root of D model before adding position information. We now have token vectors, but the attention operation has no built-in recurrence and no convolutional window. It needs a signal that distinguishes the first position from the second. Consider these 2 sequences: dog bites person and person bites dog. They contain the same 3 words, but the order changes the meaning. Without position information, self-attention has no position-specific signal that distinguishes those 2 arrangements. If we permute the input rows, the outputs permute in the same way. The operation sees token content and pairwise similarity, but no absolute or relative order unless we provide one. The original transformer adds a positional encoding to each token embedding at the bottom of the encoder and decoder stacks. The positional encoding has the same width as the token vector, 512 values. That makes element-wise addition possible. For an even-numbered dimension, the paper uses PE of position, 2i, equals sign of position divided by 10,000 to the power 2i over D model. For the neighboring odd-numbered dimension, it uses cosine with the same frequency. Different pairs of dimensions oscillate at different rates. The short wavelengths change quickly with position. The long wavelengths change slowly. To make the values visible, shrink the formula to a 4-dimensional teaching example. At position 0, the first 4 position values are 0, 1, 0, 1. At position 1, they are approximately 0.84, 0.54, 0.01, and about 1. The screen will preserve the more precise values. At position 2, they are approximately 0.91, negative 0.42, 0.02, and about 1. These are values from the paper's formula, evaluated with a 4-dimensional width for illustration. The real base model uses 512 dimensions and many more frequencies. Now watch one token vector change. Suppose an invented toy embedding, after the square root scaling described earlier, begins as 0.2, negative 0.4, 0.7, and 0.1. If it appears at position 1, we add the position 1 values element by element. The result is about 1.04, 0.14, 0.71, and 1.1. The token identity and its position now occupy the same vector. The authors also tested learned positional embeddings. Their reported result was nearly identical to the sinusoidal version. They chose the sine and cosine functions, partly because, for a fixed offset, the encoding at the later position can be represented as a linear function of the encoding at the earlier position. They also hypothesized that the fixed encoding might extrapolate to sequence lengths beyond those seen during training. The paper does not prove that this extrapolation will always work. After this addition and dropout, the source matrix enters the first encoder layer. Self-attention begins with the matrix we will call X. Each row belongs to one token position. In the base model, each row has 512 values. The model does not compare those 512 value rows directly. For each attention head, it learns 3 projection matrices. 3 multiplications create the working matrices. X times the query projection produces Q. A second multiplication uses the key projection and produces K. The value projection produces V. In the base model, one head uses these shapes. X is N by 512. WQ is 512 by 64. So Q is N by 64. WK is 512 by 64. So K is N by 64. WV is 512 by 64. So V is N by 64. The letters query, key, and value describe 3 roles inside the calculation. A query represents what the current position will use to score candidate positions. A key represents how each candidate position participates in that score. A value carries the information that will be mixed into the output if that position receives weight. The key is not a word dictionary. The value is not the final answer. Q, K, and V are learned linear projections of the current layer's input. Every layer and every head learns its own projections. The query and key decide the weights. The values provide the content that those weights combine. Keeping these roles separate lets the model learn one representation for matching and another for the information that moves. The central equation is attention of Q, K, V equals softmax of Q, K transpose divided by the square root of dk multiplied by V. We will calculate every part of that equation. We will use the first 3 teaching tokens from our source sentence, I, love, and AI. We will set the period aside so that the arithmetic fits on screen. We will shrink Q, K, and V from 64 dimensions to 2. These values are invented so that we can do the arithmetic on screen. They are not weights from the trained paper model. Let the query rows be. For I, 1, 0. For love, 0, 1. For AI, 1, 1. Let the key rows be 1, 0, 1, 1, and 0, 1. Let the value rows be 1, 0, 0, 1, and 1, 1. Take the first query, 1, 0. Its dot product with the first key, 1, 0, is 1. Its dot product with the second key, 1, 1, is also 1. Its dot product with the third key, 0, 1, is 0. The first score row is therefore 1, 1, 0. Because our teaching keys have 2 dimensions, dk equals 2. Divide every score by the square root of 2. The scaled row becomes approximately 0.707, 0.707, and 0. Now apply softmax across that row. Exponentiating the first 2 values gives about 2.028 each. Exponentiating 0 gives 1. Divide each result by their sum, about 5.056. The attention weights become approximately 0.401, 0.401, and 0.198. They are positive and add to 1. Now multiply those weights by the 3 value rows and add the results. The first value contributes 0.401 times the vector 1, 0. The second contributes 0.401 times the vector 0, 1. The third contributes 0.198 times the vector 1, 1. Adding them gives 0.599. 0.599. That vector is the new attention output for the first position. Repeat the same calculation for the other 2 queries. The full scaled score matrix is: the first row is 0.707, 0.707, 0. The second is 0, 0.707, 0.707. The third is 0.707, 1.414, 0.707. After row-wise softmax, the weight matrix is approximately: the first row is 0.401, 0.401, 0.198. Next comes 0.198, 0.401, 0.401. The final row is 0.248, 0.503, 0.248. Multiplying by V produces 3 output rows: 0.599, 0.599, then 0.599, 0.802, then 0.497, 0.752. Every output row is a weighted mixture of value rows from the sequence. The weights depend on the query at that output position. This is the mechanical meaning of attention in the equation. The model forms, scores, normalizes them, and uses the normalized scores to mix information. The scaling term can look like a small mathematical adjustment. It solves a training problem. Suppose the components of a query and a key are independent random variables with mean 0 and variance 1. Their dot product adds dk products. Under that simplified assumption, the dot product has variance dk. As dk grows, the score distribution spreads out. Large positive and negative logits push softmax toward very sharp probabilities. In those saturated regions, gradients can become very small. Dividing by the square root of dk brings the variance back toward 1 under the paper's simplifying assumption. In the original base model, dk equals 64, so the scale factor is 8. The division does not make every score small. It keeps the typical scale from growing, just because the query and key contain more components. The authors called this operation scaled dot product attention. Dot products also map efficiently to optimized matrix multiplication code, which made the operation fast and memory efficient compared with a small feed-forward compatibility network used by additive attention. One attention head creates one score matrix and one weighted mixture of values. The paper found it useful to run several heads with different learned projections. The base model uses 8 heads. Each head receives the same layer input X, but each head owns different WQ, WK, and WV matrices. Head 1 may assign high scores to one pattern. Head 2 may assign a different pattern because it sees different projected coordinates. Each head produces an n by 64 output. Concatenating 8 heads produces an n by 512 matrix. A final learned projection, WO, mixes those 512 values and returns the result to the model with. The equation is multihead of Q, K, V equals concat of head 1 through head H multiplied by WO, and each head is attention of QWQI, KWKI, VWVI. The paper uses Q, K, and V here for the inputs supplied to the multi-head sublayer. Each head applies its own projections to those inputs. In our single-head calculation, we use Q, K, and V for the already projected matrices. The operation is the same. The notation starts at a different side of the projection. The heads run in parallel. They are not 8 sequential reasoning steps. The later archive version includes appendix figures that visualize some trained heads. Those figures do not appear in the NeurIPS proceedings version. Several patterns appear related to long-distance dependencies, anaphora, or sentence structure. The wording matters. An attention pattern can be suggestive, but the paper does not prove that one head is a fixed grammar module or that attention weights provide a complete explanation of the model's decision. The ablation results also reject the simple idea that more heads must always be better. With roughly constant computation, the single-head version scored 0.9 blue below the best setting in that comparison. Quality also fell when the number of heads became too large and each head became too narrow. Multi-head attention is only the first sublayer. In the original encoder, its output enters a residual connection and layer norm. The paper writes this as layer norm of X plus sublayer of X. The residual path carries the sublayer input X directly to an addition. The attention sublayer computes a proposed change. Adding the two means the next stage receives the original signal plus that change. The width must remain 512 so that the two matrices can be added element by element. Layer norm then computes normalization statistics across the features of each position. In a simplified description, it centers and rescales that position's feature values, then applies learned scale and shift parameters. It does not average different token positions together. The placement shown in the paper is now called post-norm because normalization follows the residual addition. Many later transformer variants use a different order, but this lesson is following the 2017 architecture. The result enters the position-wise feed-forward network. The paper's equation is FF n of x equals max of 0 and x W1 plus B1 multiplied by W2 plus B2. The first linear transformation expands each 512 value position to 2048 values. ReLU replaces negative intermediate values with 0. The second linear transformation returns the vector to 512 values. This network uses the same parameters at every position within one layer. It processes each position separately. Different transformer layers use different feed-forward parameters. Attention and the feed-forward network perform different kinds of work. Attention moves and mixes information across positions. The feed-forward network transforms the features inside each position after that information has arrived. Another residual connection and layer norm complete the encoder layer. The base encoder repeats this structure 6 times. The number of token positions stays the same through the stack. The values at each position change, because every layer can combine information from the entire previous layer and then transform the result. At the bottom, the vector for love begins as a learned token embedding, plus its position encoding. After one layer, it can contain information drawn from I, AI, and the period. After 6 layers, the source positions form a contextual representation of the full sentence. The encoder does not produce the German sentence. It produces the memory that the decoder will read. The original transformer uses multi-head attention in 3 distinct places. First, the encoder uses self-attention. Q, K, and V all come from the previous encoder layer. Every source position can attend to every source position. Second, the decoder uses masked self-attention. Q, K, and V all come from the previous decoder layer, but a causal mask blocks future target positions. Third, the decoder uses encoder-decoder attention. The queries come from the decoder. The keys and values come from the final encoder output. The same attention equation appears in all 3 places. The source of Q, K, and V changes, and the decoder self-attention adds a mask. That distinction is easy to lose in a full architecture diagram. We will now watch the decoder perform both kinds of attention. During training, the correct target sentence is available. The model must still learn to predict each token from earlier target tokens, not from the answer at the same position or later positions. Suppose the target pieces are ich, Liebe, K, I, and the period. The decoder input is shifted right. Conceptually, it receives begin, ich, Liebe, and KI. The desired outputs are ich, Liebe, KI, and the period. At the first position, the decoder sees the begin token and predicts ich. At the second position, it can use the begin token and ich to predict Liebe. At the third position, it can use the begin token ich and Liebe to predict KI. Because all target positions are placed into one training matrix, the model needs a rule that prevents information from flowing backward from future answers. The causal mask provides that rule. We will reuse the same small numbers from the encoder example so that the arithmetic stays familiar. They now represent 3 decoder positions: begin, ich, and Liebe. These are new teaching rows, not the encoder's Q, K, or V tensors. Before masking, the scaled score matrix is: the first row is 0.707, 0.707, The second is 0, 0.707, 0.707. The third is 0.707, 1.414, 0.707. For the first query position, the second and third keys belong to the future. Replace those scores with negative infinity. For the second query position, the third key belongs to the future. Replace that score with negative infinity. The masked matrix becomes: the first row is 0.707, negative infinity, negative infinity. The second is 0.707, negative infinity. The third row does not change. Softmax turns the masked positions into probability 0. The resulting weights are approximately: the first row is 1, 0, 0. The second is 0.330, 0.670, 0. The third is 0.248, 0.503, 0.248. The first position can use only itself. The second can use the first two positions. The third can use all three. This triangular mask preserves the autoregressive rule while allowing the allowed positions to be computed together during training. The mask does not teach word order by itself. Positional encoding supplies position information. The mask controls which target positions are visible. Masked self-attention tells the decoder what has already been generated on the target side. It does not yet tell the decoder which English source information matters. The next sublayer performs encoder-decoder attention. Here, the decoder state produces the queries. The final encoder output produces the keys and values. Imagine that the decoder is preparing the German token lieb. Its query can assign weights to source positions. A high score on the source token love lets the corresponding source value contribute strongly to the decoder's new vector. Other source positions can also contribute. The operation is a learned weighted mixture, not a hard word-to-word dictionary lookup. Every decoder position can attend across all encoder positions. The causal target mask does not block source positions because the full source sentence is already known. This cross-attention sublayer also uses multiple heads, a residual connection, and layer norm. The decoder then applies the same kind of position-wise feed-forward network used in the encoder, followed by another residual connection and layer norm. One original decoder layer, therefore, performs this sequence. Mask targets self-attention, cross-attention over the source, then a feed-forward transformation. The decoder repeats that structure 6 times. At the top of the decoder, each target position still holds a vector. The base model width is 512. A learned linear transformation maps that 512 value vector to one logit for every token in the target vocabulary. If the vocabulary contains 37,000 pieces, the output for one position contains about 37,000 logits. A logit is an unnormalized score. It can be positive or negative, and the logits do not need to add to 1. Softmax exponentiates and normalizes the logits into a probability distribution over the vocabulary. For the decoder position that has already seen begin and ick, imagine this small teaching vocabulary and its candidate logits. Ick receives 1.1. Libby receives 3.2. I receives 0.7. Und receives negative 0.4. The period receives 0.2. After softmax, Lieb receives the largest probability. These displayed numbers are invented to show the output operation. They are not logits from the paper's model. During training, The predicted distribution is compared with the correct next token. The loss sends gradients backward through the output projection. Decoder layers, encoder-decoder attention, encoder layers, embeddings, and all learned projection matrices. The model changes its parameters so that correct target tokens receive more probability on similar training examples. The word does not emerge from one neuron. It emerges from the complete computation that produced the final logits. The transformer gains much of its training speed because many positions can be computed in parallel. On the source side, all encoder positions are available at once. On the target side during training, the shifted correct target sequence is also available at once. The causal mask prevents illegal information flow, while matrix operations compute all allowed target positions together. Inference is different because the correct future target tokens do not exist. Begin with a start symbol. Run the decoder and obtain a distribution for the first output token. Select a candidate such as IC. Append it to the decoder prefix. Run the next step to obtain a distribution for the next token. Continue until the model produces an end symbol or reaches a length limit. The paper uses beam search rather than simply choosing the single highest probability token at every step. Beam search keeps several promising partial translations. At each step, it extends them, scores the new candidates, and keeps the best few. For the reported translation results, the authors used a beam size of 4 and a length penalty with alpha equal to 0.6. They also limited maximum output length to input length plus 50 and stopped early when possible. For evaluation, the base result averaged the last 5 saved checkpoints. The big result averaged the last 20. Checkpoint averaging is part of the reported evaluation procedure, not an additional transformer layer. Beam search is an inference procedure. It is not an attention layer, and it does not change the learned transformer architecture. The output loop remains sequential at the token level. A later token depends on the prefix selected so far. The 2017 transformer reduced sequential computation during training, but it did not generate an entire autoregressive translation in one step. This distinction resolves an apparent contradiction. The model is highly parallel inside each training layer, while autoregressive decoding still advances one output position at a time. The architecture specifies operations and shapes. Training fills those operations with useful numerical parameters. The learned parameters include token embeddings and the query, key, value, and output projections used by attention. Every layer also contains 2 feed-forward matrices, a normalization scale and shift values. The model shares its embedding matrix with a transformation before the vocabulary softmax. The sinusoidal positional encoding in the original model is fixed, so those position values are not learned. The authors also tested a learned alternative. During one training example, the model performs a forward pass and produces probability distributions for target tokens. A loss function measures how those distributions compare with the correct targets. Backpropagation computes how a small change in each parameter would affect the loss. Atom uses those gradients to update the parameters. The paper used Atom with beta 1 equal to 0.9, beta 2 equal to 0.98, and epsilon equal to 10 to the negative 9. The learning rate rose linearly during the first 4,000 warm-up steps. After warm-up, it decreased in proportion to the inverse square root of the step number, with an additional scale based on D model. The paper reports this schedule, but does not test why warm-up helps, or why 4,000 steps is the best choice. A common practical explanation is that the small early learning rates avoid large updates while the optimizer's running statistics and the network's representations are still changing quickly. That explanation is broader background, not a causal result from this paper. The authors also used dropout. In the base model, the reported dropout rate was 0.1. Dropout randomly removes selected activations during training, which discourages the network from depending too strongly on one path. They used label smoothing with epsilon equal to 0.1. Instead of treating the correct token as probability 1 and every other token as exactly 0, label smoothing gives the target distribution a small amount of mass outside the correct class. The paper reports that this worsened perplexity, but improved accuracy and blue score. Perplexity and blue do not measure the same thing. Label smoothing makes the model less certain, which can worsen the likelihood-based perplexity measure even when the final translation metric improves. The English-German experiments use the WMT 2014 dataset with about 4.5 million sentence pairs. The shared source target BPE vocabulary contained about 37,000 tokens. The English-French experiments used 36 million sentences and a 32,000 word piece vocabulary. Training batches grouped sentence pairs by approximate length. Each batch contained about 25,000 source tokens and 25,000 target tokens. The base model contained about 65 million parameters. It used 6 encoder layers, 6 decoder layers, a model width of 512, a feed-forward width of 2,048, 8 heads, and 64-dimensional keys and values in each head. The big model contained about 213 million parameters. It increased the model width to 1,024, the feed-forward width to 4,096, and the number of heads to 16. The key and value width per head remained 64. The authors trained on one machine with 8 NVIDIA P100 GPUs. One base model step took about 0.4 seconds. They trained the base models for 100,000 steps, or about 12 hours. One big model step took about 1 second. They trained the big models for 300,000 steps, or about 3.5 days. These figures describe the reported 2017 experiments. They do not describe the scale of a modern frontier language model. The paper compares 3 properties: computation per layer, the minimum number of sequential operations, and the maximum path length between positions. For a sequence length n and representation width d, a full self-attention layer has complexity on the order of n squared times d. A recurrent layer has complexity on the order of n times d squared. The comparison depends on the relationship between n and d. The paper notes that self-attention is computationally favorable when n is smaller than d, which was common for sentence representations in the translation systems being studied. The stronger advantage concerns sequential operations. A recurrent layer requires n sequential steps because each state depends on the previous state. A self-attention layer can compute all position pairs with a constant number of sequential stages at the layer level. The matrix grows with n, so the total arithmetic and memory do not stay constant. Order 1 sequential operations does not mean order 1 total work. Path length gives another view. In one self-attention layer, any position can exchange information directly with any other position. The maximum path length is constant for that layer. In a recurrent layer, connecting the first and last positions may require a path through n recurrent steps. A local convolution needs multiple layers to connect distant positions unless its kernel covers the full sequence. The short path, can help the model learn long-range dependencies. It does not guarantee that every trained head will learn the dependency we want. Full self-attention also carries a cost. The score matrix contains n-squared entries. As sequences become long, memory and computation grow quickly. The paper recognized this issue and mentioned restricted attention as a direction for longer inputs. On WMT 2014 English to German, the big transformer reached 28.4 blue. The paper reports that this exceeded the best previously reported results, including ensembles, by more than 2 blue points. The base model reached 27.3 blue on that test, while using less estimated training computation than every competing system in the paper's comparison table that reported an estimate. The English to French number needs a version label. The official NeurIPS 2017 paper reports 41 blue in its abstract, Table 2, and Section 6.1. The 2023 archive version 7 reports 41.8 in the abstract and Table 2, but Section 6.1 still says 41. The documents therefore disagree. We should not quote one number as though every version contains it. For the historical conference result, 41 is the internally consistent number in the official NeurIPS paper. The later archive revision displays 41.8 in 2 prominent locations and leaves 41 in the body. The later archive version adds an English constituency parsing section that is absent from the NeurIPS proceedings paper. A 4-layer transformer performed competitively with limited training data and reached 92.7 F1 in the reported semi-supervised setting. This experiment supported the claim that the architecture could generalize beyond the 2 translation benchmarks, though it did not establish performance across every sequence task. The paper changed individual parts of the base model and measured English-German development performance. Reducing the key dimension hurt quality in the reported comparison. The authors interpreted this as evidence that computing compatibility is not easy, and that a more sophisticated compatibility function might help. Increasing model width generally improved performance in the reported comparison. The 1024 wide variation produced higher development blue than the base configuration, while a 256 wide model performed worse. Depth did not improve every tested model. The 8-layer variation scored below the 6-layer base result on this development set. Dropout helped avoid overfitting. Removing it reduced development blue in the reported experiment. Replacing sinusoidal positional encodings with learned positional embeddings produced nearly identical results. The number of heads had a middle range that worked best in this ablation. One head performed worse, and making the heads too numerous and narrow also reduced quality. These are controlled variations within one experimental setting. They show what happened in the reported model and dataset. They are not universal laws that fix the best number of heads, width, dropout rate, or position method for every transformer. We can now audit the title against the machine we just followed. Attention moves information between positions. The transformer still needs several other operations. Tokenization turns text into discrete pieces and IDs. Embeddings turn IDs into learned vectors. Positional encoding provides order information. Query, key, value, and output projections learn how each head represents matching and content. Softmax converts attention scores into normalized weights. The feed-forward network transforms features within each position and supplies a nonlinear ReLU in the original model. Residual connections preserve a direct path around every sublayer. Layer norm controls the numerical representation after each residual addition in the original postnorm design. The output projection and softmax produce next token probabilities. The optimizer, learning rate schedule, dropout, label smoothing, data, and loss make training possible. So the literal sentence, "attention is all you need," is false as a component list. As a research claim, the title says something narrower and more important. An encoder-decoder sequence model can achieve state-of-the-art translation without recurrent or convolutional layers, using attention as its main mechanism for communication across positions. The paper did not invent attention. Earlier sequence-to-sequence systems already used attention, and the paper cites that history. Its contribution was a full sequence transduction architecture built around attention without sequence-aligned recurrence or convolution. It introduced and combined the specific scaled dot product and multi-head design, position representations, residual structure, feed-forward sublayers, and training choices that made the transformer work well. The paper did not prove that attention weights provide a complete explanation for a prediction. The appendix added in the later archive version shows patterns that appear related to linguistic structure. Those figures are observations, not a guarantee that one attention map exposes the model's full causal computation. The paper did not remove all sequential computation. Its autoregressive decoder still generates output symbols, one at a time, during inference. The paper did not present the exact architecture of GPT or today's chat systems. The original transformer is an encoder-decoder model designed around translation. Decoder-only language models retain causal self-attention and other transformer ideas, but they remove the separate encoder and cross-attention path. Later systems also changed position methods, normalization order, activation functions, attention implementations, and many training details. Knowing the 2017 machine remains useful because its central data flow is still recognizable. Token vectors enter learned projections, queries, score keys, normalized weights, mix values, position-wise networks transform the results, and stacked layers build contextual representations. The transformer mattered because it changed the route by which information travels through a sequence model. An RNN carries information through a chain of states. The transformer lets positions interact through attention matrices that can be computed in parallel during training. The famous formula is compact. Softmax of QK transpose divided by the square root of DK multiplied by V. Its operation is concrete. Queries and keys make scores. Scaling controls the score distribution. Softmax makes weights. The weights mix values. Everything around that equation makes it usable as a complete model. Positions, multiple heads, residual paths, normalization, feed-forward transformations, a decoder mask, cross-attention, and a vocabulary output. Once you can follow those numbers, the architecture diagram stops being a wall of boxes. It becomes a sequence of transformations, resta that you can inspect, calculate, and implement. In the next lesson, we can go one level deeper and build a tiny attention layer in code, or move forward to the decoder-only transformer used by GPT-style language models. Tell me which path you want, and subscribe to continue from zero to AI expert.